Hello there. So today we're going to cover this one simple concept called the filter method transmitter, more exactly SSB filter method transmitter. So there are actually two types of upconversion using for frequency upconversion for single sideband signals. Today we're going to particularly look at the filter method transmitter. So SSB obviously stands for single sideband transmitter. So for filter method, what we have here, we have two ways to go about doing the filter method. And the first one, the simplest one, is the single conversion, and the other one is the three conversion. So the only difference between them is, from a top-down view, is that the three conversion just splits these three digits of frequency into three separate blocks. It adds them one by one. So some of you might ask, why do we need three exactly? The thing is, we don't actually always need three conversion, because it's just a convention that usually the frequencies that you want are within 3 digits of accuracy. So for example, 22.1 here, which means that you can get away with having 3 separate conversion steps. So you can add 0.1 first, and then you add 2, and then you add 20 to get 22.1. So yeah, from a top-down level, the functional difference between single conversion and three conversion is that single conversion upconverts in one step, in a single step, whereas the three conversion obviously upconverts your frequency in 3 steps. Okay. Also, there's also another difference that I'm gonna go through later. First, we're gonna start with the three conversion. Even though it's the more complicated one, trust me, I think it's gonna be a better way to introduce this topic. So we're just gonna go ahead and look at the circuit that we have here. So this is in its full glory. In its full glory, your three conversion filter method circuit. So I just want you to notice that you have 3 balanced modulators and BPF units. So that's 1, 2, and 3. So these 3 units are actually just 3 separate single conversion units. You will see them later. You will look at them later. With the exception of the summer here. Now, in this syllabus, you would actually see this summer for 3 conversion specifically, but note that you don't actually need this summer. You can just remove this summer block, and your output would just be a single sideband suppressed carrier signal. But if you want, for purposes of demodulation, a reduced carrier instead, of course you can add, usually you just add the summer block here. So all the summer block does is it re-adds the carrier frequency that's been removed from the modulator. Okay, so let's go one by one. I guess the best way to go about this is to look at a sample question while referring to the circuit. So this is your sample question. So we're going to ignore the values from the figure here, and we're going to use the values from the question instead, which means that now we have the frequency is going to be split into 3 frequencies that we're going to add up. So those frequencies are 100 kilohertz. That's the first frequency we're going to add. Then 4 megahertz, and finally 30 megahertz. All right, so this is going to sum up to, in the end, it's going to sum up from 34.1 to 34.104. We're going to go step by step. So these are your modulating frequencies. Your carrier frequencies. Your modulating frequencies are going to be from 0 to 4 kilohertz, which we're going to represent using this triangle here. So this would be your modulating band of frequencies. So 0 to 4 kilohertz. So now it's looking at what the frequency spectrum looks like at the balanced modulator 1 output. So what does that mean? What you have here is this dotted line means that your frequency, your carrier frequency component is gone. It was there, but it's gone now. That's what the dotted line means. It means nothing. Like, it means that there is no carrier frequency component, right? So the thing is really simple. You add 100 kilohertz. So from 0 here, you just add 100 kilohertz. 4, you add 100 kilohertz to that, so you have 100 and 104 kilohertz, and this is just 100 minus 4 kilohertz, so you get 96 kilohertz. But of course we don't really care about this because we're gonna put it through a bandpass filter anyway. So that brings us to the next output, your BPF output. So that's going to remove your lower sideband, and you're going to get just 100 and 104 kilohertz, so that your frequency is unchanged. This thing needs to be here because you need to signify that it is an single sideband suppressed carrier signal. So that's why you need, it's suppressed. The carrier signal is suppressed, so you need to signify that there is no carrier frequency component. So after the summer output, we're gonna reintroduce the carrier frequency signal at a lower power, usually 10% of its unmodulated power. So we're gonna call this SSBRC. So that R actually stands for reduced, right? Reduced carrier. But in our case, you can also look at it as representing reinserted carrier, because it's literally the same carrier frequency from your local oscillator that's just added back, reinserted at a lower power. We're not going to go into why we do that, but we're going to go it's going to be covered in the demodulation section later. Okay, so after the summer output, it's going to go through the balance modulator to output, and what this does is, again, it adds your second carrier frequency, 4 megahertz, to your input frequencies of 4.1 and 4.104. 100 and 104 kilohertz. So these are your input frequencies. So again, we do the same thing as in balance modulator 1, with the exception that you can see that this is getting wider. This is actually an advantage. Why is it an advantage? It's because you can have a bandpass filter that's soft. What do I mean by soft? A hard bandpass filter, you can think of an ideal bandpass filter as like a box, right? So it's very hard here. So of course, ideal bandpass filters don't exist. They always have some sort of curve to them. So something that looks like this is a hard bandpass filter, right? But if you have a more relaxed slope, for example, like this, maybe I'll get a better color, maybe turquoise. So if it looks like this, it's more relaxed. So that's what we call a soft bandpass filter. So you can use a soft bandpass filter, which is usually less costly, to do your frequency upconversion instead, right? Because now doing this in steps makes this gap here that doesn't contain any useful information. So that allows you to use a cheaper bandpass filter. So that's, so it's just the same math. 100 plus 4 kilohertz, so that's 4.1, and so 0 plus 4 megahertz, so that's where you get this gap here. Again, bandpass filter to output, you remove this, right? But you don't actually include this thing here. Why? It's because your output signal at BPF2 is already SSBRC. It's already at reduced carrier. There's a reduced carrier component here that's reinserted. So you don't draw this. Don't forget this. You need a notch. Like, it has to be a solid notch. Don't do it like this, because like making it in dots means the absence of your carrier frequency. So this solid line means you still have some carrier frequency signal there. It's just at a reduced power. Balance modulator 3 output is the same thing, except that your carrier frequency now is different. It's now at 30 megahertz. So now you just add 30 megahertz to 4.1. That's 34.1 megahertz. 4.104. That's 34.104 megahertz. Again, it's the same thing. Again, you see this widening of like a gap in the middle. Again, we've gone through why that is advantageous. So again, at BPF3 output, you ignore this thing. Just take this one, but don't forget your reduced carrier frequency here, right? Okay, that's short line. So that's it. So we've gone through all the 3 conversion circuit already. So let's test our understanding by looking at what happens if we have a single modulating frequency input at 1.5 kilohertz. So what would be the frequency that will show up at the output of our BPF1 then? That would be just summing up 100 kilohertz, right? So that would be 101.5 kilohertz. At BPF2, you add your previous frequency, that becomes your input, and add 4 megahertz. Now you have 4.1015 megahertz. Again, you repeat the same thing. You add this frequency, right? You add it with 30 megahertz, which is your third carrier frequency. And again, now in 3 steps, you get 34.1015 megahertz. But what if you want to skip all these steps and just, have one step? So that's where single conversion, conversion filter type comes in. So you do all that addition in one step. So for example, in this question, it's a frequency carrier of 28 megahertz. So you add 28 megahertz in one step. You don't decompose it into 10, 10 and 8. You decompose it into you don't decompose it at all. You just add 28 megahertz. So again, it's the same thing. Your modulating band comes from, varies from 0 to 3 kilohertz, and your carrier frequency is 28 megahertz. So it's the same thing. You just add, 28 to 0 and 28 to 3 kilohertz. So you end up having 28 megahertz and 28.003 megahertz at the output of your mixer. So right after that, so right after the BPF, you just end up with, what you just saw, except that since this doesn't have that summer into it, the type of signal that you're gonna get is SSBSC, suppressed carrier, because you didn't reinsert the local oscillator, that carrier signal, back into your BPF output. Your mixer output. So that's about it. Now the second question is, what if you have a single 2.2 kilohertz modulating signal input? Again, that's the same thing. You just add 28 megahertz. So you're going to end up with 28.0022 megahertz. Now we're going to go through a second question. This is a little bit tricky. So this is an SSB transmitter. The question wants, what if you have this SSB transmitter, right? And you have a microphone input here, which is actually a carrier signal, except that this carrier signal actually varies, the frequencies vary in time, because that's your audio input. So let's just assume that whatever audio you're gonna pick up, it's gonna be within 300 to 3300 hertz. So what does that mean? First, we draw an audio band spectrum. So your microphone bandwidth is 3 kilohertz. So it starts at 300, ends at 3300. So let's look at the center frequency of this audio band. So that adds up to 1800. So this is just simple math, calculating the distance. So that's 1800 hertz. So what happens if you have this carrier signal here, which is actually your audio input, and you mix it with a carrier signal of 9 megahertz? I'm sorry. Okay, that's actually your... Sorry, I got it flipped. Your audio in is actually your modulating signal, and your carrier signal is 9 megahertz, of course. So what does that... What happens when you mix it with the carrier frequency? And of course, we know that for lower sideband, the question specifies lower sideband, which means that it's FC minus your frequencies that you have in your modulating circuit. So that will be FC minus 1800 in the middle, FC minus 300 in the left, and FC minus 3300 on the right. So this would be the output of your mixer. This is the lower side of your mixer output. So you should actually draw the upper side band as well, but to simplify things, this is what your lower sideband looks like. So what happens when you put it through a bandpass filter? So that's the thing. We don't actually know what the frequency response of this bandpass filter looks like. All we know is, what would it look like? What would it look like if it just fits your lower sideband your lower sideband signal. So now it's asking, what is the approximate center frequency? How do we find out? How do we find that out? So let's first assume that your bandpass filter is ideal. So this is the blue thing that I drew. That's your ideal BPF frequency response. So we're assuming that it just fits your mixer output, right? And what that means is the center frequency of your bandpass filter is the exact same as your center frequency of the lower side of your mixer output. So that is FC minus 1800. So that is approximately your filter center frequency. So FC minus 1800 is just 9 megahertz minus 1800. So that gives you 8.9982 megahertz. So that's about it. I hope everything's clear enough. You can always feel free to rewind. I think that's about it. Actually, there's another for single sideband upconversion. Other than the filter method, there's also the phase shift method, but we're gonna cover that in a later video. Okay, thank you for watching.